Welcome back to day 3. Just a quick recap on the activities from day 2. We have written a complete batch analysis script doing cell counting using loop and array. So we can now set the input and output folder, get the file list to run a loop, and we can use either with or without the batch mode. We also know how to make a proof image and save it along with our image analysis result. Also, we have learned that clearing up the workspace and memory is important when processing many images in batch. On day 3, using the second example of image analysis, which is the file converter script, we will use the components we have used in example 1, and we will learn more components from there. This example is focused on file handling and contain many useful segments such as automatic generation of output folder, filter file name from array, handling raw microscope images using bio format, and handling multidimensional stack. So in this file converter script, we will first select the input folder, which is the file converter folder under the demo images. In the previous example, we then have had to select an output folder manually, and we can actually make this process automatic, so we can only select the input folder and let image J to generate the output folder. After we cover this, we will look into the contents of the folder, and in the previous example, we have only TIFF files nicely arranged in a folder. But in a real example, our folder may contain all different types of files. Or we may want to select a specific group of files. So as a third step, we will practice on how to filter out the files we would like to use based on the file name. In this demonstration, I'm also going to filter and use one of the raw microscope image format, which is .lif, rather than the TIFF images. Using the raw microscopy file format in image analysis is advantageous because it contains more metadata of our acquisition settings. And also we can avoid unnecessary duplication of our dataset. But the most of raw microscopy format requires bioformat plugin to be opened in ImageJ. So as a fourth step, we will go through on how to use this bioformat plugin in our script. In many cases, when we image our sample, we take images as various dimensions. For example, we can just take a single channel, single plane images, or multi-channels if you have multiple labelings, or Z-stack for three-dimensional information, or even a time-lapse for live cell imaging. This example image contains such various dimensional images, and once we open each series, we will process images based on its dimension to make a representative image for each. For example, if the image has multiple channels, we will first split channels, and if the image is a Z-stack, we will make into a maximal intensity projection. And if the image is a time-lapse, we will make a small montage using the first two time frames. After this, we will set the color and label each image and rename it and save as JPEG in the output folder, which we have generated automatically. In this workflow, as you can see, I have added many components in one script to show you what is possible, and hopefully you can grab some segments out of this and utilize in your own script in the future. So now we know the entire workflow, let's go and start writing this step by step. And don't worry if you have missed any steps or need more time to digest information. As similar to previous days, you can replay this video from our YouTube channel or follow the instruction PDF to work at your own pace this afternoon. The first step is to select the input folder, and we can now easily do this using get directory function. When the dialog pops up, we will select the file converter folder under the demo images folder. Then we will work on the segment which will generate an output folder automatically. When we select File Converter folder under the Demo Images folder, the indir path will end something like this: demo images / file converter /. This slash at the end is there because we have selected a folder. Then we are going to composite a new path string based on this indir. So it is the same until the demo images and /, but the folder name is different so that it has the original folder name with additional word after that, such as output. This will also end with / as this will be also a folder. Once we have this string, we can let image_j to make a new folder using a function called file.makeDirectory. And we can add the path inside this bracket. So how can we make this out dir path from the indir path? We can do it with few different functions. The first function we can use is the file.getParent function. This function will return the parents of the file, which is specified by path inside this red bracket. Essentially, this will give us the full path of the upper folder of indir, which is up to the demo images. The caveat of this function is that this will give us the string without the / at the end. So we have to add a / by ourselves. We can do this using the function called file.separator. And as you can see from this description, this will return the file name separator character either as / or \. Different operating systems will use either / or \, so it is safer to use this function rather than using it as a text. Then we can get the folder name of the input folder. The reason for this is because we want to make our output folder name rooted from the input folder name. This will make it easier to identify our output folder rather than simply name it as output, as otherwise we will soon end up having many folders named as output. The function to get folder name is file.getName. This will return the file name from the path, and again it will be file converter without /. This is handy this time as we will add an additional word after this, and in this case, space and output. And then we can finish this with /, which is a file separator. All of these values can then be glued together using plus operator to make a full string. And for each functions, we can assign the return value into variables. In this way, we can reuse this if we ever need to later on. So I have assigned file separator into fs, path of the parents into upper folder, name of the folder into folder name, then add it all together in the correct order and assign to a variable called outdir. So we can use this outdir in the function file.makeDirectory. All of these processes are dependent on the indir value, So this get directory line also can be put together as a complete component, and I can add comments at the top. When we test this, we have to run these all 6 lines together from the get directory until the make directory line. And once I select the source folder, we can check that our output directory is generated automatically. The next step we will work on is to filter the files based on its name. In many cases, our input folder may contain different types of files, and this will make it hard to run batch if we just try to open any files in the folder. If you remember the batch plugin we have covered in day 1, there was also the option to filter files based on the file name. So we are now trying to add this function in our script. So first, we can grab the entire file list in our source folder using the getFileList function as shown in day 2 example. And we will assign the list of files into a variable named as list1. So you can think that each file name is now stored as elements in array named list1. Then this is what we are trying to do, that get another list that is filtered showing the only .lif file. So the next thing we will do is to make a new empty array with the same length as list1 using new array function. When we make a new array, the value of each element will be automatically assigned as 0. We can check inside our array using function called array.show. And please note that this function is somehow color-coded as black, although it is a built-in function. This array.show function is very useful as this shows the elements of array in a table format with the array name as title and also shows multiple arrays as multiple column. So what we are going to do is now to run a for loop for the length of our array and inspect each element in the list1 array. So for loop can be written this way, and in there we can check if each element is ending with .lif text using ends with function. This ends with function will return true if string inside the red bracket ends with the suffix we put it there. There are also similar functions we can use for strings such as start with, index of, substring, and matches, and you can find more information from the built-in function website. Then if the string does ends with .lif, we can copy that to our list too. And it is written this way. The index of list1 is I, but this list2 will have a different index to the list1, so we will use A as a different index. And we can define A at the outside of the for loop. And then whenever we find .lif files and add to the list2, this value will also go up. So we can add this A++ after this. Then we can close this if statements and the for loops. When the for loop is finished, our list2 will have one element in the first index and the rest will be still zeros. So as a final step, We have to trim our array using array.trim function. This function will return an array that contains the first n elements of array. So we can use A as our cutoff point because this A was increased only when the elements was assigned to list 2. So this function will trim the list 2. We can also double check the contents of our array at this step using array.show function. And now you can see that the list 2 now has only .lib files. So now we have the list that contains lib file only. We can open this file in ImageJ. Lib file is the raw microscopy format from Leica microscope, and in ImageJ, we can use the bioformat plugin to access images inside the raw files. When you drag and drop your microscopy image, and if you have seen this pop-up window, then you've been already using the bioformat plugins. And this means if we would like to open this type of images using the script, simple open commands, which we used before, will not work anymore. So we'll have to know how to call it using bioformat script. Bioformat plugin works this way. When we drag and drop the raw microscopy image, if it is readable from the bioformat, this window will pop up, which is on bioformat importer. We can set many different import functions from here, and when we click OK, it will either open image or opens additional dialog window, which is the series option window showing multiple images. Microscopy file format like LIF contains many different images, so this will show different images in the list. Other format like Zeiss microscopy format will store the large dataset in a series of different resolution. So this will show the same image in different frame size in the list. Either way, we can add this bioformat importer into our script, so we can run batch automatically without manually selecting these options. The easiest way to use bioformat plugin in our script is to record the step. When you have the recorder open, and open the images by dragging and drop and select option, this step may not be recorded at all. To record bioformat import process, we have to go to Plugins, Bioformats, Bioformats Importer, and then select the image we want to import. After we have gone through the same import options, now we can see the options have been recorded. So this is what was recorded when I was opening our leaf image and select the first image in the series. It is a very long text, but you can see that the majority of it is the file path inside this box bracket. And in our script, we will assign our file path as variable, so this can be shortened this way. So let's try add this on our script. From the previous step, this is what we have done so far. On the first paragraph, we have generated output folder automatically. And on the second paragraph, we have filtered the file using two arrays. So the list 2 is the array which we can use for the next loop. So after this, we can start to make our file opening loop using the list 2. And our file path will be input directory plus the elements of the list 2 array. We can then add our bioformat importer recording. If the string is still too long, we can also break into multiple segments using plus operator. And when you break the strings, make an extra care to keep all the empty spaces, as otherwise the full string will not be read properly. In this code, other than the recordings of import options, which are mostly the default setting, the last part here shows which series we have selected. If I have selected the second from the series window, this value would be 2. If we are going to select the first series on the list all the time, we can leave it as it is, and this will only open the first series of every file. But in this case, we want to iterate the loop to open each series at a time. So I'd like to make a for loop to go through all the series inside the current for loop. And as I have used I already, this loop will have a j as a counter. And we are going to iterate this for the total number of series, which we will define on the next step. And now I can replace this series number as my loop counter, which is j. And also because my loop counter will start from 0, while the series counter will start from 1, I can add 1 on this counter variable to match to the series number. So the next step is to find out how we can get this total number of series using bioformat. Bioformat plugin supports a lot more scripting options. If you go to this website, you can see more information, and one of them is the macro extensions. We can get the details of macro extensions from ImageJ through plugins, bioformat macro extensions. Similar to the built-in function website, this will show you the entire functions available for the macro extensions on the log window. And from this extensive list, I will use few core functions on our script. The first function is ext.setID. This will initialize the extension with given ID inside this bracket, and this is where the file name goes, so we can use our file path variable here. And another one is the ext.getSeriesCount, and this will get the number of image series in the active dataset on the variable inside the bracket. So I'm going to use this extension, but we'll set the variable name a bit shorter as series. All of this extension function always has to be placed after this run command. So this is what we have so far after I have added comments. When we start a batch loop using list2, we can set the file path and start the bioformat macro extensions, and then set the image for the extension, then get the number of series of that image. Based on that, we can set up another loop, and we can use our importer commands which we have recorded. In this code, if we are using the default import options, these long commands can be also replaced using macro extensions. One is ext.setSeries, which will set the current series, and another one is ext.openImagePlus, and this will open the image at the given path with the default options. As you can see, the amount of information it requires to open image is the same, but this way is a lot simpler. Also note that the series count starts from 0 in this case. So this is the script we have so far. We already have gone through the first part up to line 20. And this is the second part where we have covered the bioformat macro extensions. Now, if we run from the first line up to here, line 43, this will open the first series image of the leaf file. Or if we close the loop for this series temporarily and run, this will open all series and we can inspect what kind of images are there. Our microscopy images can be taken as various dimensions. So this example image contains such various dimensional images to demonstrate different processing options based on its dimension. On each series, if the image has multiple channels, we will first split the channels. And if the image is a Z-stack, we will make into a maximal intensity projection. And if the image is a time-lapse, we will make a small montage using the first two time frames. To do so, we will need to know the dimension of the image. We can get the dimensional information of our image using getDimension functions. This function will return the dimensions of the current image as width, height, channels, and slices for zip line, and frames for the time frames. From the opened image, we can also get the full title of the image. When we open the image with bioformat, the image title will include both file name and the series name. So we will get the full name using getTitle function and store as window name. If you remember from day 1, we can check the value of our variables using debug window, and we can access to it by making intentional error by typing any undefined variable like this. When we select this image and run these 3 lines, we can see the values of all variables. And the dimension of this first image is 512 and 512 in width and height, and 111 for the channel slices frames. The third series in this image has 3 channels and 89 Z slices. So when we run this code, we can check the values for this image. So the first thing we will do is to select the opened image and split the channels. One thing we also have to think about is that we also have some single channel image in the series, and when we try to run split channel on the single channel image, we will get the error and the script will stop there. So we need to set up a condition that this runs only if it is a multi-channel image. Now let's have a look at the split images. After split, the title of split images will have prefix added based on the number of channels. So there is C1-, C2-, C3- added. And if we are going to process each split images, we have to figure out how to call each image. So if our original name was stored in variable window name from the getTitle function, the name of the split image can be made using the uppercase C plus the number of channel plus the dash in front of the window name. For the channel number, we will start our channel loop with 0 with counter as k, so we will also add 1 on the counter to make the first channel number as 1. Then we will store this in the variable called channel name. Later, when we save the representative image of these images, we will add the channel number as suffix because this will make us arrange files better. We can make a new name in a different order, that the window name comes first, and then add -c, and then plus the channel number, and store in a variable named as saving name. So to summarize what we have done so far after the image is opened is first get the title and the dimension of the image, and split channels if it has more than one channel. And because we will process G-stack or time-lapse on each channel image, we will set up a loop to iterate each channel like this. And then we will select the specific channel window to process. From there, we already have identified how the name of split images are going to be. So we can define that name inside the loop. And also based on that, we have made a saving name for file saving later. So we can also put it here. And we can also define on what's going to be used as a channel name and saving name if the image was not split. In this case, it can simply be the same as the original title, so we can just define it this way. Then we can set the condition using if and else statements. So once we have selected a single channel image to process, we will run max intensity projection if it's a Z-stack. And we will make a montage if it is a time frame, or nothing if it is a single plane image. But I have made this last else part so I can use it for other code. Max intensity projection can be recorded via image, stacks, Z-project. So our recording will look like this. And montage making can be recorded via image, stack, make montage. Setting the column as 2 and rows as 1 will make the final layout to contain only 2 images regardless of the total Z slices. Then we can also keep the image as the same scale as original and add a borderline between images for easier visualization. We will also label each image using label slices option with font size at around 20, and this font size is best to be tested on your own images to find an optimal value. We can also use the foreground color as our font color. So here's our recordings. So now we have this processing script. As a final step, we will set the style of our output image and save as a JPEG in the output folder which we have generated automatically before. When the multi-channel image is split, sometimes the original lookup table will be retained, but sometimes not. And if you like this grayscale image, you can save as it is, but if you don't like it, we can also apply color. We can set many different type of color from image lookup table. And if we have selected red, this is what will be recorded. Also, when we have many channels, we can also preset the list of colors we would like to use as an array and call each element for each channel. And once we have set the color, we have to convert our image type to RGB image, so the color scheme is retained outside the image J. We can record these commands via image, type, RGB color. Lastly, on the RGB image, we can also write any text using drawString function. This function draws text at the specified location with a filled background. In this case, I have set the write value assigned to label variable and set the location as 10 pixels from the left, 40 pixels from the top, and also I have set the background as black. And this is because I have set the font color as white using setColor function. This function sets the drawing color as indicated in the bracket. And here are the list of colors we can use. Also, I have set the font style using setFont function. This function sets the font used by the drawString function. I have used sans serif font and set the font size as 30 and set the style as anti-alias to make the font clearer. Regarding how to use this labeling in various styles, there are very useful demo scripts in the built-in function website, so please try if you're interested more on this. And regarding which text to draw on each image, we can define at our if-else statements used previously. At each category, we can define variable label with different strings such as MIP, time-lapse, single plane. So the representative image will be labeled based on the original dimension of the image. So once we have the final image to save, we can save it to our output directory with the saving name we have made earlier. So to summarize what we have done so far after the image is selected, we have processed zigzag or time-lapse on each channel image. And when we do that, we have also defined what we are going to label it as. Then we have set the color of our image and set the style of our label and then saved. So we're done with all the processes. We can close the loop and also clear up the workspace and memory and finish all the loops. So this is the end of day 3 for macro writing workshops. Like yesterday, there is only one activity for you to do before tomorrow, which is to complete this example by yourself. Thank you for your attention.